Okay, Math 2017 question 1A. We actually covered this in one of the Problem Solving Matters videos, if you caught those, but I'm including it here for completeness. So we're given this cubic and we're asked whether it has two distinct real stationary points. The thing I think of when I read that is I should probably try and look for the stationary points. That's something I know how to do for a cubic. And okay, this one involves this letter K, but I'll think about that when I get there. So for stationary points, I should think about f of x being equal to 0. So here I'm going to have to, the derivative of f of x being 0. So here I'm going to differentiate f and get 6x squared minus 2kx plus 2. I want that to be 0. This is a quadratic in x, and I want it to have two distinct real stationary points. It's easy to get excited and think quadratic, that means two roots, so all values of k definitely got two real roots. Of course, if you think about it, we know that some quadratics don't have two real roots. The thing we're supposed to check is the discriminant. If the discriminant is positive, then your quadratic has two distinct real roots. Here the discriminant is this, and that is positive. So that's the discriminant is positive. And it's positive if, let's simplify this a little bit, k squared divided by 4, 2 times 6 is 12, k squared is bigger than 12. That happens in two different ways. Either if k is bigger than 2 root 3, taking the square root, or if k is very negative, if it's less than minus 2 root 3. K squared is big when k is very negative or when k is very positive, where here very means compared to 2 root 3. Okay, that is option B. So 2017, question 1A, my answer is B, these two ranges of values of k. In this question, we've got a function that we'd like to minimize. We'd like to find the minimum value of this function. Normally when I see minimum value, I think about differentiating. I think about the derivative with respect to x and setting that equal to 0. But here there's cosine x in my function. And at maths, we don't expect people to know how to differentiate cosine x. If you're doing maths and further maths, at some point you'll learn how to differentiate cosine x, but that's not how we intend people to do this question. You're welcome to go and differentiate cosine x if you know how to and you want to do it that way, but there's other ways to do the question that do use maths on the MAT syllabus. Okay, if I stare at this a bit, it starts to look like that trick where there's a quadratic, but the thing inside the quadratic is also a square, if that makes sense. That sometimes you see these things like 9x to the 4 minus 12x squared plus 7, and it looks like a quartic fourth degree polynomial, but actually it's a quadratic of x squared. Here, this looks like a quadratic in cos squared. You know, I've seen a lot of quadratics before, and I like spotting quadratics. So I'm going to try and write this as if it's a quadratic, as something like 9 cos squared x squared minus 12 cos squared x plus 7. Okay, and something I know that you can do with quadratics is you can complete the square. That's sometimes helpful because then once you've completed the square, the variable only appears in one place in the expression. So we can start thinking about maximising or minimising that expression. Let's try and complete the square here. So it's going to be 3 cos squared x. I'm going to write a number here, aren't I? Something like minus 2, because that will give me times 2 minus 12 cos squared x. It'll give me a 4 though, so I need to add on 3. Okay, so now my challenge is to find the minimum value of this function. I need to be a little bit careful here because the minimum value of the function might come when 3 cos squared x minus 2 is a small positive number or a small negative number. I'm worried about this squared sign. That's caught me out on similar questions before, where I need to remember that positive and negative numbers can square to the same thing. That can be confusing. Okay, so I'm a little bit worried about that. The 3 doesn't matter for finding out where the minimum is. It's going to change the minimum value, I suppose, but it's not going to change where the minimum happens. Now let me see. So, what do I know about cos squared x here? Well, I suppose cos squared x, I could write that in terms of sine squared, but then I've got a similar question about sine squared, so I'm not sure that helps very much. Let me just think. That would be 3 minus 3 sine squared, so the 3 and the 2 would combine together a bit, but not very nicely. I'd have a sine squared. Okay, I'm not even going to write that down. I suppose I know that cos squared x is somewhere between 0 and 1. Could be 0, could be 1. So 3 cos squared x is somewhere between 0 and 3. Okay, is this helpful? Well, I suppose I can keep building outwards, right? So 3 cos squared x is somewhere between 1 and minus 2. Sorry, minus 2 in here. If I subtract the 2 as well. 3 cos squared x, let's write that again. 3 cos squared x minus 2 is somewhere between 1 and minus 2. Now, when I square this, I'm going to get things... It's not going to be true that it's 4 less than or equal to the square of this less than or equal to 1. Squares are funny, remember. Squaring negative numbers gives you positive things. Okay, so you can't just square each side of this equation. In particular, if I want a small number after I've squared, and I want to square something that's near 0, I suppose the question is, can I square 0 when I do this? And I think I can. If cos squared x was equal to 2/3, then this square bit in here, 3 cos squared minus 2, this term inside the brackets would be 0. So then I get 0 squared plus 3. You can't do better than that, right? Because if you make this thing inside the bracket negative or positive, then when you square it, you'll get something bigger than 0. So this is the minimum I can do, I think. 0 squared plus 3. Can I do cos squared as 2 over 3? Yes, I can, because cos squared takes all the values between 0 and 1. Okay, so I can achieve this value, which makes my answer A. Okay, question 1c. We're given a sequence. We're told the first couple of terms. A1 is 2 and A2 is 6. We're asked for A 2017. I don't think that we should go and work out the first 2017 terms, but it's probably a good idea to work out the first few. I'm always encouraging you to work out the first few terms of a sequence when you're given a new unfamiliar sequence. Here the rule is that an plus 1 is equal to an divided by an minus 1 for every n bigger than or equal to 2. So that includes the case n equals 2, when this would say A3 is equal to A2 over A1, if I put n equals 2 into that expression. Or if I put in n equals 4, then I'd get A4. Sorry, if I put in n equals 3, then I get A4 is A3 divided by A2. And so on. Each term is supposed to be the ratio of the previous two. So A3 here is A2 over A1. We've been told A2 and A1. That's 6 over 2, which is 3. And then I can work out A4, because that's now A3, I now know, is 3. And A2 is 6. So this is 1/2. Okay, can I see a pattern in these numbers? Is it a geometric series? 2, 6, 3, 1/2? No. Is it an arithmetic sequence? No. So I don't recognise this sequence. So I'm a bit stuck. I haven't got any great ideas. I'm going to keep working out terms and see if I have any ideas. Worst case scenario, I'll keep working out terms until I hit A 2017 without having any good ideas, and then I'll have the answer to the question. So that's something to look forward to. How long's this video? Do I work out all of the terms? You tell me. A5 is going to be A4 divided by A3, which is going to be 1/2 divided by 3. That's 1/6. What have I seen? So I've got 2, 6, 3, 1/2, 1/6. Is the next term 1/3? Just sort of like 1 over the previous things. A6 is A5 over A4, which is 1/6 divided by 1/2, which is 1/3. So that's pretty good. We've got this 2, 6, 3, 1/2, 1/6, 1/3. A7, let's do the next one. Let's see what it does next. It's going to be A6 over A5. That's going to be 1/3 over 1/6, which is 2, I think. And then A8 So now it's gone 2, 6, 3, 1 half, 1 6, 1 third, 2, and I'm hoping it's going to be 6 next, because I've sort of seen this kind of 2, 6, 3 pattern going on. A8 is A7 over A6, which is 2 over 1 third, which is 6. And now I've got a 2 and a 6, and I can relax now because each term only depends on the previous two. So once I hit this 2 and 6 again, now it's going to repeat, because now we're going to do the same calculations again, right? When I try and work out A9, I'm going to do A8 divided by A7, that's 6 over 2. That's going to be the same answer as what it was back over here when I did 6 divided by 2 to work out A3. So A9 is going to be equal to A3, and A10 is going to be equal to A4. I'm going to do the same calculations again. I'm not going to do them on the screen, but in theory we're doing the same calculations again. So this repeats every 6 terms. Okay, so I need to work out how many times we've gone round, or where we've ended up when we get to 2017. So I suppose I need to divide 2017 by 6, work out what the remainder is to work out what would have happened after we've gone around a certain number of times. So 6 goes into 21 3 times, leaving remainder 3. 6 goes into 37 6 times, remainder 1. I think 2016 is a multiple of 6. Quick check, it's even and it's a multiple of 3. 2017 is 1 more than a multiple of 6. 1 more than a multiple of 6 means I think that it's going to end up being the same sort of thing as other things that are 1 more than a multiple of 6, like A1, that was 1 more than a multiple of 6 and that was 2, or A7, 7 is 1 more than a multiple of 6 and that was also 2, repeats every 6. When we get around to A2017, 2017 is 1 more than a multiple of 6, so we'll hit 2 at that point as well. So I think the answer is D. Okay, nice transformations of curve question here. We're given the graph y equals f of x, and we're asked which of these is y equals minus f of minus x. So to make minus f of minus x, 2 transformations have happened. There's this transformation inside here that represents a reflection in the y-axis, and there's a reflection as well in the x-axis that's flipped this graph upside down. So we need to take this picture, reflect it in the y-axis, reflect it in the x-axis, and then we'll get our answer. So, okay, if we reflect it in the y-axis, we get a picture like this, coming down and then going up, and a bit over here, going down. That's f of minus x. And then we'll reflect it in the x-axis, this thing going up and going down over there, and a bit over here, like that. And that's going to be minus f of minus x. Okay, quick check. It's definitely not D or E, which don't have the right shape at all. Do I think it's A or B? No, neither of those match my picture. I think it's going to be C, as the one that's minus f of minus x, just from my picture that I've drawn here. Fun extension question. Can you guess what this function is in the picture? I'll give you a clue. It's something like ax plus b over x minus 1. Something like that. I think where a and b are different numbers. Okay. Here's Matt's 2017 question 1e. We're told that we've got 2 positive integers, a and b, that add up to 20, and we want to maximise a squared b. So sometimes when I see a squared b, or when I see maximise, find the maximum value, I think about differentiation. I think about taking that derivative and working out what the maximum value is. Here the function is, we're only allowed to put in integers. So I've got this problem that if the maximum of this sort of combination of a's and b's, if that doesn't happen at an integer, if there's a different value where the gradient is 0, I don't really know what to do next. Maybe we'll think about it that way though. Okay, so if a plus b is 20, then I can eliminate b, I think. I don't want to think about this restriction separately. I just want to use it to say, well, I get two positive integers, a plus b is 20. I'm just going to write b is 20 minus a, and use that to just get rid of b's. Then the thing I'm maximising is a squared 20 minus a. And I want to find the maximum value of that, but a's got to be a positive whole number. Okay. So I suppose I could think about this. I could think about drawing a picture of this. I know that if it's only defined on whole numbers, then really that's more like a bar chart or something, but I'm going to try and draw it like it's a polynomial, like it's the polynomial 20a squared minus a cubed, I suppose. That would look like, well, so near 0, this goes through 0, 0. Near 0, a cubed is very small, so this looks like 20a squared. And then it's got another root, so it's got a repeated root at 0, and it's got another root at 20. Okay, so if I could take a to be anything I like, then I'd take a to be something in the middle here. This is some cubic equation, it's got a maximum around here. If a has to be a positive integer, I suppose I want an integer that's round about there. Maybe, because it's quite flat near there, it's hard to tell whether maybe I want an integer just to the left or maybe an integer just to the right. I don't want an integer value of a that's further away than that, I think. Because if I go further away, then this starts decreasing. So I want either the integer to the left or the integer to the right, if I'm only allowed integers. All the others feel like bad choices because I start going sort of down the hill. I don't want to go down the hill to look at other integers. I definitely don't want to put 20 in. If you put 20 in, you get 0. That's not the maximum. It's not even any of the options. Okay, so let's try and find this point on the cubic. It might not be the right answer because it's probably not going to be an integer, but I feel like we should try and find it. Okay, so let's call this f of a or something. That's what this picture is. And then work out f prime of a, which is a bit of a strange thing to write down for a question about whole numbers. Anyway, 40a minus 3a squared, when I differentiate it, I want f of a to be 0. That happens when a is 0, or when 40 minus 3a is 0, or 8 or 0. I'll write that down. So that says I want a to be 40 over 3, which is 13 and a third. Okay, so what I said before is either I want the integer to the left or the one to the right. They've both gone down the hill a little bit, which I suppose I've got to go down the hill a little bit so that I hit a whole number. This is not a whole number. Let's just check those two. So let's check a equals 13 versus a equals 14. Those are my two candidates. I suppose in that case b would be 7, in this case b would be 6. If that matters, I'm going to work out a squared b. So here a squared b is 169 times 7, and here a squared b is 196 times 6. It's not obvious to me which of those is bigger, so I'm going to have to work them both out. 63, 7 6s are 42, 48, 7, 11, 1183. Or I could have a equals 14, in which case I'll get something like 54, 57, 6, 1176. 1183 is slightly bigger than 1176, so I want this one. I want 1183, which is option D, and I noticed that 1176 is included as option C. So that's a little bit sneaky, but I can make 1183 by taking a to be 13, b to be 7. Okay. Question 1f here asks us to think about values of x with tan x less than cosine x less than sine x, and they've shown us those regions on the unit circle where I think The coordinates are cosine x and sine x. That's what you get when the angle is x, right? Because then the hypotenuse is 1, it's the unit circle, and then the x coordinate is cosine x and the y coordinate is sine x. Right, I suppose it's not the x coordinate if the angle is x. That's a bit strange. Let's think about different values of x and then work out later which of these regions corresponds to the answer to this question when are both of these inequalities true. Okay, so I need to think about cosine x less than sine x to start off with. I'm also going to think about tan x less than cosine x. I think cosine and sine are easier to work with than tan and cos. Okay, let's try and draw both. Cos does something like this, and sine does something like this. So cosine is smaller than sine in this region, which I'm going to try and draw now. This region between here and here. That's the bit where cosine is smaller than sine. Otherwise, cosine is bigger than sine. Okay, I need to find out what those angles are at the end there. I think they're points where the lines cross, so they're points with cosine x equal to sine x. That happens if your opposite and adjacent sides are the same, right? So here's an example of a triangle with cosine and sine equal. So that's a 45-degree triangle. It's one of my standard triangles, I think. Okay, and then I suppose if I add 180 degrees, then cosine and sine both change sign, because when you add 180 degrees, everything flips over. That's one of the symmetries of cosine and sine curves. So I think this end here is 225 degrees. The point where cosine and sine are both equal to minus 1 over root 2. Okay, so that's some range where the first inequality is true. It's between 45 degrees and 225 degrees. I think on the graph, 45 degrees would be somewhere over here, and 225 degrees would be somewhere over here. So I think not A and not E, because they don't satisfy this second inequality. Those ranges seem like they're out. I want x to be between 45 degrees and 225 degrees. Okay, and I'm not quite sure if this is 225 or not. I'm not really sure if these are 45 degrees or not. Okay, so 3 candidates left, B, C and D. And I've got to think about tan x being less than cosine x. Okay, so a bit tricky to draw tan and cosine at the same time. Let's give it a go. Cosine stays between 1 and minus 1. It's quite well behaved. Comes down to minus 1, goes back up to 1 again. I'm trying to leave some headroom to draw tan. Tan is going to increase, isn't it? So it starts at 0. It's going to increase. There'll be some point with tan equal to cosine. And then tan gets really big until we get to here, where tan's not defined. There's a vertical asymptote. And then tan comes back in again, very negative values. Goes through 0 here, when cosine is minus 1. And then shoots up to very large values, not defined again when cosine is 0 over here. And then comes back from very negative numbers up to 0 again. Okay, so tan is less than cosine in a couple of places. Tan is less than cosine over here, and tan is less than cosine in here. Well, tan's very, very negative over there. And then also over here. So lots of angles to find for this inequality. I knew this one would be harder. This is so this asymptote is 270 degrees, and this is 360 degrees. And actually, there's no overlap between this interval and the ones I found for the other inequality. So none of that. It's all over here somewhere. I'm not interested. I want both of these inequalities to be true. Over here, I think I've got some points, haven't I, where tan is equal to cosine. I'm interested in this first bit. I'm not super interested in 0 because it's not in my first interval. In fact, let's try and put 45 degrees on this chart. So at 45 degrees, tan is 1 and cosine is 1 over root 2. So 45 degrees is an example of a point around here where tan is already bigger than cosine. So I think that means that this region over here, where tan starts off small, that's limited to very small angles, smaller than 45 degrees, so there's no overlap between this region and this interval. The only bit of overlap is going to be this bit here, which starts at 90 degrees and goes up to some other angle. Starting at 90 degrees and going up a bit to some other angle is a perfect description of region C. So I think my answer is C. Let's try and find out what that angle is. So it's an angle here where tan x is equal to cos x. And both of them are negative. That's a description of this point down here. I've got tan is sine over cos, so I could write sine x is equal to cosine squared x. Then I could use cosine squared is 1 minus sine squared to get, this is 1 minus sine squared x, sine x. I'm going to rearrange this. It's starting to look like a quadratic. Sine squared x plus sine x minus 1 equals 0. And try and solve that to get sine x is minus 1 plus or minus root b squared minus 4ac. Really? Yeah, 1 minus 5 all over 2. I want a negative thing for my value of... What do I want negative? Let me think. I've got cosine is negative and sine is... I probably want sine to be positive, don't I? Because I'm somewhere between 90 degrees and 180 degrees. So I want sine to be positive. I want sine positive so that tan and cosine can both be negative. Sine is positive at here if I take the plus sign. So sine x is minus 1 plus root 5 over 2, which is not quite the golden ratio. What's the value of tan x in that case? I'm going to have to go back and work out, do I want to do this? Yeah, I'm going to have to go right around. I should have eliminated sine maybe. So that's cosine squared x. Do I want to work out cosine x? So cosine x is going to be the square root of root 5 minus 1 over 2, which does simplify, but I'm going to leave it like that as the value. The value for x just around here. It looks like it could maybe have been 135 degrees. That's not quite 135 degrees in that picture. Okay. Okay, question 1G, and this is from back in the days when the questions used radians. So you could imagine where it says 2 pi here, you can imagine that saying 360 degrees if you like. Okay, so for all theta in that range, it's quite a sensible range of theta, this line, y minus 1 cosine theta, I suppose if theta is a number, then this is y minus 1 times a number is equal to x minus 1 times a number, divides the disk x squared plus y squared less than or equal to 4 into 2 regions. And already this sounds a bit unbelievable, like I want to draw a picture just to find out what's going on with this. Let a of theta denote the area of the larger region. Okay, so we've got 2 regions and we want the larger region, whatever that means. Then a of theta achieves its maximum value. We maximise the size of the larger region at 1 value of theta, 2 values of theta, 3 values of theta, 4 or all of the values of theta. Maximise its value at all the values of theta. That sounds a bit strange. I suppose that would be if it was constant or something, if it didn't matter what theta was. Let's try and draw a picture. So this x squared plus y squared is less than or equal to 4. I know what that is. That's a circle of radius 2. So this is my x direction and this is my y direction. And I've got this circle of radius 2. They've told me this is a line. It's not obviously a line, I think. I suppose if these two things are just numbers, if I'm taking some particular value of theta, then I've got y minus 1 times a number is equal to x plus 1 times a number, and that kind of looks like there's no squares in there, so it doesn't look like a circle, it feels more like a line. Let's try and work that out. So maybe if I rearrange it a bit, it'll look more familiar. So if cos theta is not 1, if cos theta is not 0, then I'm going to rearrange this to be x plus 1 sine of cos is tan theta. So y is 1 plus x, let's multiply that out, 1 plus x tan theta plus tan theta, I suppose. Okay, so we've got some y-intercept, y at 1 plus tan theta, and we've got x tan theta, gradient tan theta. Okay, so that looks more like a line now. I think I believe it's a line. What points does it go through? Well, I can see from this form that when x is minus 1, y is 1. Let's try and mark that on here. So when x is minus 1, y is 1. That's a point inside the circle. Because it's a distance of root 2 from the origin, and root 2 is less than 2. Okay, so this point's on the line, and tan theta is the gradient of the line, which I think means thinking about the gradient of the line here. So sort of dy by dx is tan theta. I think that means I could write something like this for theta. So I think this is the relevant triangle to draw, right? If the gradient is tan theta, then you could draw a little diagram like this. This is the line with gradient tan theta, the one that makes an angle of theta with the x-axis. I think this triangle makes sense. Opposite over adjacent really is tan theta. Okay, that's me trying to defend drawing this line and saying that the gradient here, or the angle above the x-axis, is theta, and the gradient is tan theta. Okay, so now it's starting to make a bit more sense. There's this point, 1 minus 1, that always lies on the line, and as we change theta, we get different lines that go through that point. Let's try and draw some of them. So this is one particular value of theta, but if I increase theta a little bit, then I can get a line like this. If I make theta go the other way, theta a bit larger, I could have a line going the other way. And in each case, for each particular value of theta, we're going to call A of theta, I'd like to think about this now, we're going to say A of theta is the area of the larger region. Okay, so the larger region, I suppose, is the one, if the line splits the circle perfectly in two, so if the line goes right through the middle, then neither side is actually bigger than the other. I suppose you could take either region in that case to be the quote larger region. If the line is at a bit of an angle, then I think one side will end up being larger than the other. How would I make the big area really big? Let's draw a special picture. So I'm imagining kind of drawing the line. If the line's like this, this is kind of the dead center line. If the line's like this, then as you change theta here, you'll get a big bit of circle, a big chunk of circle, and you'll lose a little chunk of circle from moving it around like that. And I suppose that keeps working until you get round to a point where, like this, where this is at right angles to that line through the centre of the circle. Because now, as I continue changing theta, I'll pick up an area on this side, and I'll lose an area on this side, and I'll pick up an area on this side as I rotate that line, and I'll start gaining more area on the other side of that bit. So I think it's a picture like this, where I've taken the line to be at right angles to, I suppose that dotted line is joining that point to the centre of the circle. That's going to be the kind of greedy way to make the larger region here have the maximum possible size. Okay, so in this case, A of theta is going to be the biggest it can possibly be. If this line's at a little bit of an angle, then it feels like I can level it off to be at right angles to that dotted line to make A of theta slightly bigger. Okay, the question says, how many values of theta are there that correspond? No, A of theta achieves its maximum value at, and then sort of how many values of theta. And I suppose there's a bit of a trick, because I've talked about this value of theta giving me this line, but actually I think I could rotate that line 180 degrees. So I could rotate 180 degrees if this is theta. I could rotate 180 degrees, and then I'd have this being theta. 180 degrees bigger. If I do that, then I get the same picture. The line rotated by 180 degrees gives you the same line. And still, A of theta is going to be the area of the larger region. So that's going to be the area on this side again, which is it's going to take the same value. So putting this all together, I think that if you take theta to be 45 degrees or 225 degrees, I think you get a maximum value of A of theta. I don't know what that area is. I don't really want to work it out. Luckily, it doesn't ask me to. It just asks me how many values of theta are there that give the maximum value of A. And I think there are 2 values of theta. Okay. Okay, this question is about factors of polynomials and remainders. I'm going to try and use the factor theorem. So we're given 2 facts about some polynomials. The first one is that x squared minus 2ax plus a to the 4. If you try and divide that, we're told, by x plus b, so if you write that as quotient of x times x plus b, then you get remainder 1. So in algebra, that's what the first sentence means. If you try and divide this polynomial by x plus b, then you get some quotient and a remainder, and we're told the remainder is 1. Okay, first fact we're told. The second fact we're told is that bx squared plus x plus 1 has ax minus 1 as a factor. I'm going to need a different letter of the alphabet here, but I'm going to go for capital Q for a different quotient. Ax minus 1, okay, as a factor, so no remainder. So that's for some Q, big Q of x, some other quotient. Okay, and I'm not told what these quotient polynomials are. I'm told about the remainders, but not the quotients. So probably my strategy is going to be to try and work out some equations to relate a and b to each other that don't involve q or the other q at all. I'm going to try and eliminate the q's if I can by, I suppose I know these facts are true for all x. That's the nice thing about factorising polynomials. You don't just do it for a particular value of the polynomial, you're factorising the polynomial for all x. So I can choose special values of x. I can choose x wisely so that I can get rid of the q's. This is sort of the factor theorem, but I'm showing all my algebra just that you can see how it works. In the first one, I'm going to set x equals minus b. In the first one, let's call this equation 1. This is equation 2. I'm going to set x equals minus b in equation 1 because that kills off this bracket. X plus b will be 0, so that'll make this term here 0. And then I don't need to work out what little q of x is, or I don't need to say anything about q of x. It will just go away and leave me with a factor that's got a's in it, maybe b's, or maybe not. Yeah, maybe some b's. Let's find out. So if I plug in minus b, then I'll get b squared plus 2ab plus a to the 4 is equal to 0 plus 1. Okay, so you see that's giving me a nice equation relating a and b. In the second one, I'm going to set x equal to 1 over a in 2, because I can see that makes the bracket 0. 1 over a times a is 1, take away 1 is 0. So that's going to give me b over a squared plus 1 over a plus 1 is going to be equal to 0. Okay, great. So now I've got 2 equations relating a and b together, and my job now is to solve these equations. Let's multiply that second one up by a squared. I want to get rid of the fractions, I think. So the second one there is going to be b plus a squared is equal to 0. Okay, so that I suppose gives me b in terms of a. If I knew a, then I could work out b. Let's use it to eliminate b, I think. So b is equal to minus a squared. So if I plug that into the first one, so plug into, I need to number some more equations. Plug into 3. This is equation 4. Plug that into equation 3, and I'll get, oh goodness me, a squared plus a squared plus 2a a squared plus a, excuse me, minus sign. B is equal to minus a squared. 2a squared plus a plus a to the 4 is equal to 1. Is this going to be nice or is this going to be nasty? This is going to be nasty, isn't it? So that's going to give me 2a to the 4. 2a to the 4 minus 2a cubed. So let's multiply out this bracket first. A to the 4 plus 2a cubed plus a squared, and then it's going to be minus 2a cubed, minus 2a squared plus the a to the 4 I put on the first term. Minus 1 equals 0. Okay, I've noticed that these a cubed terms cancel, which is really nice because that gives me 2a to the 4 plus a squared, minus a squared minus 1 equals 0. Which is a quadratic for a squared. I've seen this sort of thing before where it's a quadratic, it looks like a fourth order polynomial, but secretly it's a quadratic for a squared. Here I think the solutions are 2, so let's try and factorise that. 2a squared, let's put an a squared over there. I want a minus sign here and a plus sign there. So then I get 2a squared plus 1. 2a squared plus 1 is not 0, but a squared minus 1 could be 0. A could be 1 or A could be minus 1. Okay, let's check very quickly for what B could be. Then B would be minus 2 in this first case. If A is 1, let's write this over here because it's relevant over here. If A is 1, then B is minus 2. If A equals minus 1, then B is equal to... If A is minus 1, then B is 1. Take away 1 minus 1. B minus 1 minus 1 is 0. 0. So B can be minus 2 or 0. That's option B for the values of B. Okay, so my answer to question 1H is B. Question 1I. This is a question about logarithms. The logarithms have slightly different bases, which is quite exciting. And there's some brackets and indices going on in here. This is testing laws of logarithms and indices. We are asked when this equation has a repeated root. So we're going to be careful. Need to be careful not to divide by anything that could be 0 in case we lose a root along the way. This language about repeated roots, and to be honest, this b squared equals 4ac thing is reminding me of quadratic equations, so I'm sort of hoping that this is somehow something to do with a quadratic equation. I really like questions where it turns out to be a quadratic equation halfway through. Let's think about that first term first, because I've seen something suspicious going on there. There's this law of indices, right? I'm going to put square brackets in just to keep track of which brackets are which brackets. My handwriting's a bit bad, so drawing different shapes is good for my brackets. Okay, law of indices, that's equal to b, so b to the x to the x. The rule here is you multiply the indices together, so this is going to be b to the x squared. And log base b of b to the x squared is just x squared. That's what logarithms do. So this is going to be x squared. Okay, this is reinforcing my idea that this might be secretly a quadratic in disguise. Okay, what else can we do? Let's try and simplify the other terms as well. So log a, c to the x over b to the x. I've now basically decided that I want this to be the linear term in a quadratic. Maybe it's not, but maybe it is. Okay, so that's going to be log base a of c over b to the x. So here I'm combining indices together, which is x times log base a of c over b. And I don't know what log base a of c over b is. I haven't really been paying attention to what a, b and c are, but hey, look, we've got this x out the front, and this is some number, I assume. Okay, and then there's a constant term at the end that I suppose is a constant term. Do I want to tidy that one up at all? I might, if I feel like it, I might move a minus sign out of this one, because logarithm of 1 over number is minus logarithm of the number. Yes, I might do that. Okay. So let's simplify that. And I'm going to write above the equation my simplified version. Okay, I've got x squared plus x log base a of c over b plus log base a, I haven't done it, log base a c is 0. Okay, that's a quadratic now. It's got pretty strange coefficients, but I can talk about where its repeated roots are, because I know a rule for when things have repeated roots, if they're quadratics. I know that you're supposed to check the discriminant. The thing that we normally call b squared minus 4ac, but a is not a, b is not b, and c is not c in this particular quadratic, because a, b and c are all combined together into the different coefficients of this quadratic. Okay, hang on a minute. I've realised I was about to get the quadratic formula out, or the discriminant or something, but I've realised that maybe I can solve this quadratic. It seems a bit unlikely, doesn't it? But the thing about solving a quadratic is you need to find things that multiply to give this, which really looks like it's the product of two things, right? These two things multiplied together pretty clearly, and add up to give this. And I was thinking about that minus sign already. You know, I think this might be x, I want to say x minus log base a of b, x plus log base a of c. I think. Because then the constant term there will have the minus sign in, and the x term will have a log base a of c and also minus log base a of b. I think that works out, using a lot of facts about combining logarithms together there, secretly behind the scenes. So actually I can solve this quadratic, I can factorise it. Using a discriminant probably works as well. My roots are log base a of b or log base a, let's do the trick again, 1 over c. Okay, so those are my two roots. It's a repeated root if these two numbers are equal. So these things are equal if and only if logarithm's an increasing function. I want b to be equal to 1 over c, so that these two logarithms turn out to be the same thing. Or said differently, c is 1 over b, which is option D. Okay, so I was expecting to use the discriminant there, or to write down the quadratic formula or something, but actually, because of logarithm rules, we can solve this quadratic and just say, well, I found the two roots. I want them to be equal. Cool. Okay, 2017 1J. Here are 5 horrible integrals. We're told not to calculate any of them, but we're asked which of them has the largest value. So I think it's interesting here to think about what on earth we can say about any of these integrals. Over here, for example, sine to the 100x with respect to x. Do I know anything about sine to the 100x? Can I try and sketch sine to the 100x? I guess when you raise numbers between 0 and 1 to the power of 100, they get quite small. 0.5 to the 100 is tiny. So I think sine x looks something like sine to the 100, and then sine of minus 1 is going to be like this again, getting up to 1, but mostly being down near 0 between 0 and pi. Oh, these questions are from back when Matt used radians, so we should imagine in here, where it says pi x, that's in radians. This is in radians as well, I suppose. Okay, so what can I say about this integral? I don't want to do that integral or work out that area at all. I'm told not to. But I suppose it would fit inside, the value's less than 1, right? All the way between 0 and pi. So I suppose I could say that this area is bigger than 0 and less than that rectangle I've just drawn with height 1 and width pi. The function kind of fits inside that box, so I suppose this is between 0 and pi. This is a rectangle of height 1 and width pi. Okay, and I think it's much closer to 0 than pi, but I haven't proved that yet. Okay, what other integrals have we got? What else do I want to look at? So sine cubed x minus 1, that one, I've just been thinking about powers of sine. I think sine cubed x is also, I suppose it's between minus 1 and 1. So this is between minus 1 and 1. So if I subtract 1, then this thing in the brackets is between minus 2 and 0. So it's negative. 108 doesn't change the thing, it makes it more negative. We're integrating between 0 and 8 pi. I don't mind. This is negative, right? This one's positive, and this one's negative. So this can't be the largest one, because c is a positive number and e is a negative number. Okay, so that's given us a way to say, I can't do either of these integrals, but I can tell you which ones has the largest value, because one of them's negative. Okay, I wonder if that helps us at all. This one's got a power of 6 in it. Anything to the power of 6 is positive, so this is positive. This one's got a cube in it, so I'm suspicious. But I suppose that 2 makes all the numbers really big. In fact, this is big, right? So 2 plus cos x is between, this thing inside the brackets is between 1 and 3. It oscillates between 1 and 3. When I cube it, I'll get numbers that are between 1 and 27. And 27, if I include the cube as well. The stuff in there is between 1 and 27. So I've got this function. I don't really want to think too much about what it's doing. Its value is between 1 and 27. When I integrate it then, I suppose, let's draw a picture. Let's try and draw a picture. 2 plus cos x cubed is going to, this is not an accurate picture at all, but just from what I've said, it's somewhere between 1 and 27, and it does something in between. But I could draw a rectangle. I could draw a rectangle up to the top line there, or a rectangle that's, that rectangle includes all of the area. Or I could draw a rectangle underneath the lower line, and that area is definitely all in the integral. So I suppose the integral here, b, is somewhere between 0 to 2 pi. Okay, so this is somewhere between 2 pi, it's less than option b, it's less than, maybe these could be equal, less than 54 pi, 27 times 2 pi. It doesn't actually take the value 27 constantly, so when you integrate it between 0 and 2 pi, I don't think you can actually get 54 pi. But hey, that's like a bound on what the integral is. It's somewhere, this integral is somewhere between 2 pi and 54 pi. Just thinking about how big the function is. Okay, what else can we do? Over here, I've noticed that x squared minus 4 is negative, right? Between 0 and 2, because x squared is smaller than 4 between 0 and 2. Sine to the 8 pi x is positive, but we're integrating a negative thing. If you integrate a negative thing, you get a negative number. Okay, so this is pretty good. We found 2 negative ones. We've got one that's somewhere between 0 and pi. This one's between 2 pi and 54 pi. Oh, I suppose that means that b is definitely bigger than c, because b is bigger than 2 pi, and c we thought was less than pi. Okay, d, what have I said so far? I know it's positive, and it's only up against b at this point. B is somewhere between 2 pi and 54 pi. Okay, let's do the same thing. Let's think about bounds on 3 minus sine x. 3 minus sine x. 3 minus sine x is somewhere between, I guess you could subtract 1 or you could add 1. So 3 minus sine x to the power of 6 is somewhere between 32 and, I don't want to work out 4 to the 6, but some huge number. And so when we integrate it between 0 and pi, 3 minus sine x to the 6, we'll get something between 32 pi if somehow this took its minimum value all the way through. I don't think it does. If this took its minimum value all the way through between 0 and pi. Or if it was really close to being its maximum value all the way through, it could be as big as 4 to the 6 pi. This one seems pretty big. In fact, I think we've just shown here that d is bigger than 32 pi. 32, 2 to the 6, 2, 4, 2, 4, 8, 16, 32, 64. Oh. I think we've shown that d is bigger. I can't work out 2 to the 6. I think we've shown that d is bigger than 64 pi, but b was less than 54 pi, which means that b is less than d because b is smaller than a thing that's smaller than the thing that's smaller than d. So my answer is D. That one's the biggest. I don't know how big it is. I've got some crazy bound on it here between 64 and the square of 64 times pi. Crazy. Right, okay, but my answer is D. In this question, we're given an equation for alpha. We're told that there's a unique real number that satisfies this equation. I guess it looks a bit like the equation for the golden ratio, if you know about that number. Anyway, the question doesn't ask us to work out what alpha is. It's about 0.755. And it doesn't ask us to prove that there's a unique number that satisfies this equation, a unique real number anyway. It just asks us to show that alpha is somewhere between 0 and 1. So here what I think I'd do is I'd imagine the graph of y equals x cubed plus x squared. That's sort of the left hand side, right? So this alpha cubed plus alpha squared thing. I'd imagine this cubic equation. Well, okay, so if I try and draw that, that goes through 0, 0. Has y equals 0 at x equals 0. And y equals 2 at x equals 1. It's got a repeated root at 0, and then it's got another root at minus 1. So that would look like this. That would be the cubic y equals x cubed plus x squared. And now I suppose all I need to say is that if I want this cubic, x cubed plus x squared, to be equal to 1, somewhere in between 0 and 2, then because x cubed plus x squared is increasing between 0 and 1, there's one value in there somewhere between one value in there with y equal to 1. So there's one value in here somewhere with y equals 1, and that's the value of alpha. That's alpha. Okay, so the web solution for MAP 2017 on the MAP website does some inequalities instead to talk about bounding this when alpha's not in this range, to say, well, if alpha's bigger than 1, then this thing's bigger than 2. If alpha's negative, then something else happens. But I think this is good enough to say this cubic increases from 0 to 2, it's going to go through 1 somewhere in between. Okay, so that's part 1. Part 2 asks us to show that, and all I know about alpha, remember, is that alpha cubed plus alpha squared is 1. I guess I also now know that alpha is between 0 and 1. It asks me to show that alpha to the 4 is minus 1 plus alpha squared. Okay, my plan here, I suppose, is to work out any fact I can about alpha to the 4. So I know, I suppose, that alpha cubed plus alpha squared is 1. That's the fact they've given me. I could multiply both sides by alpha to get this fact about alpha to the 4. Alpha to the 4 plus alpha cubed is alpha. That's not quite the fact that they want me to get. I mean, this is true, but it's not the fact they're going for because they don't want any alpha cubes in here. So I want to get rid of this alpha cubed. Here's the idea, I suppose. I know a fact about alpha cubed. It's this fact again. It's the only thing I know about alpha, so it's the only thing I can use to simplify this equation here. This alpha cubed is going to be, I suppose, 1 minus alpha squared. It's going to be equal to alpha. If I take this equation, rearrange it for alpha cubed, and plug it in over here, then I think I can rearrange this. So take this expression, rearrange it to get alpha to the 4. Alpha to the 4 is minus 1 plus alpha squared. Okay, so Before we had alpha cubed is equal to 1 minus alpha squared. That was some expression for alpha cubed. Now we've got some expression for alpha to the 4. I think we could keep going. We could keep multiplying by alpha and using different things to simplify our results down. And in fact, that's the rest of the question. So in part 3, we're given different expressions in alpha, and we're asked to find a quadratic that equal. So with integer coefficients here. So we're looking for something like number plus number times alpha plus number times alpha squared. Those are supposed to be whole numbers, and we've already seen alpha cubed can be written like this because alpha cubed is 1 minus alpha squared, and we've seen that alpha to the 4 was minus 1 plus alpha squared. Okay, so we've seen a couple of examples of writing things to do with alpha in this way that makes them equal to a quadratic in alpha. Okay, in each case below, find the quadratic expression in alpha. Okay, so we've got 4 things to do, and they're all going to be quadratics in alpha in disguise or something. We'll need to be a bit clever, I suppose. Okay, that fact we had at the start of the first part, it's off the top of the slide here, but the fact we had at the start was alpha cubed plus alpha squared is equal to 1. That's the fact we know about alpha, and we're going to try and adapt that fact. Okay, 1 over alpha, what can I do for that? I suppose when I see 1 over alpha, I'm imagining dividing by alpha. So my first idea for A was to divide by alpha. I'm not sure what I'm dividing by alpha. Hopefully something with a 1 in it. I guess I could divide this thing by alpha. If I do that, then I get alpha squared plus alpha is equal to 1 over alpha. If I divide the original equation by alpha. Oh, and that's good enough, isn't it? That's a quadratic with A is 0, no constant term, B is 1, and C is 1. So that's good. Okay, divided by alpha was the right idea. Maybe I could have divided this one by alpha, and then I'd get minus 1 over alpha, which I can fix with a minus sign. I could have 1, I'd get an alpha, so that's looking pretty good. I'd get an alpha cubed, and then I'd use the previous fact to get rid of that. So probably lots of different ways to make a 1 over alpha by dividing something by alpha. Okay, 3 part B asks us about this infinite sum. 1 minus alpha plus alpha squared minus alpha cubed plus alpha 4 minus alpha 5. And this is a geometric series, so with common ratio minus alpha. So my first term here is 1, and my ratio is minus alpha. I had to look a bit and work out that the minus signs do work out that this is a geometric series with ratio minus alpha. But I've seen a similar geometric series before, so I recognise this one. So my sum to infinity is going to be 1 over 1 minus r is 1 over 1 plus alpha. Okay, that feels like progress, but it's not it's not a quadratic. It's not in this form that we wanted. I need a 1 plus alpha. Where am I going to find a 1 plus alpha? I suppose I can see a 1 plus alpha over here. So there's sort of a 1 plus alpha hiding in here, right? 1 plus alpha is alpha. This is alpha squared, alpha plus 1. So 1 over 1 plus alpha is going to be equal to, if I divide by 1 plus alpha, it's going to be equal to alpha squared. Which, using this fact again, which is a quadratic with A equals 0, B equals 0, C equals 1. Okay, quadratic again, but here the main idea for this one was geometric series gives me a way to do this sum. And then spot some way to use the previous line. Again, probably loads of ways to use 1 plus alpha in here. I sort of noticed this 1 minus alpha squared is like a 1 minus alpha, 1 plus alpha. Maybe I could do something with that. Or maybe I'll save that for a moment, because we've got away with this 1 plus alpha thing. And in a moment I'm going to want this 1 minus alpha, aren't I? For part C, which has this 1 over 1 minus alpha. Okay. Awkward. Okay, so 1 over 1 minus alpha. I suppose I could use this to get rid of a 1 or something. I actually quite like. Can we go down this route? I factorised this 1 minus alpha squared with the difference of 2 squares. So here I know, for part C, I know that 1 plus alpha times 1 minus alpha is equal to alpha cubed. And I know a fact about 1 plus alpha as well. Maybe this is not going to go anywhere, but I know that 1 plus alpha is 1 over alpha squared. Okay, is this going somewhere? So 1 over 1 minus alpha is going to be 1 over alpha to the 5. Ugh, I'm not sure how I feel about that. I don't like that very much at all. How am I going to simplify that? 1 over 1 minus alpha is 1 over alpha to the 5. Yeah, I think I've done that right, dividing through. I'm going to need to, if I'm going to go down this route, I'm going to need to divide something by alpha to the 5. How much do I want to do that? Not a lot. Let's see. So I could take this expression up here. Alpha cubed is equal to 1 minus alpha squared. I could divide it by alpha to the 5, and I'd get 1 over alpha squared is 1 over alpha to the 5 minus 1 over alpha cubed, but I don't know either of those things either. Okay, let's try and work these things out. So if I'm going to work out 1 over alpha to the 5, I'm going to need to know 1 over alpha squared and 1 over alpha cubed. I'm going to go for it. I'm going to divide this first one by alpha squared to get my expression for 1 over alpha squared. That's going to be 1 plus alpha. And to work out 1 over alpha cubed, well, I'm going to divide by alpha again, so I'll get 1 over alpha plus 1. But that is, so 1 over alpha was a previous part of the question. We had 1 over alpha was alpha squared plus alpha. Okay, so now I've got 1 over alpha squared and I've got 1 over alpha cubed. And I know that 1 over alpha to the 5 was 1 over alpha squared plus 1 over alpha cubed, which is then going to be equal to 1 plus alpha squared plus alpha plus 1, which is alpha squared plus 2 alpha plus 2. That's my answer for 1 over 1 minus alpha. Part D has an infinite product again, and it looks a bit different. It's 1 plus alpha squared, 1 plus alpha to the 4. This is not a geometric series, I think. Maybe it'd be a good idea to work out what happens if I multiply some of the brackets out. I could try multiplying out those first couple. So if I multiply out these first two, I get 1 plus alpha squared plus alpha cubed. That's kind of nice. I get each power of alpha, right? Because I get small powers of alpha from this one, and then once I've got up to alpha, I get the powers of alpha which need an alpha squared in them. I can pick up an alpha squared and an alpha cubed. Okay. That's kind of nice, multiplying out the first couple of brackets. I guess I know 1 plus alpha from some previous parts of this question. What about if I multiply it by 1 plus alpha to the 4? So I've noticed 4 is the next number, isn't it? So again, this 1 is, when I multiply out by this 1, it's going to give me some small powers of alpha, and then the alpha to the 4 will be just enough to give me some next powers of alpha. So this bit, these first 3 terms, will multiply to 1 plus alpha squared plus alpha cubed, plus, and then alpha to the 4 times everything I've got. Alpha to the 4 plus alpha to the 5 plus alpha to the 6 plus alpha to the 7. And then, look, there's an 8 here, so that's going to do the same thing when I multiply the next bracket. It seems like the biggest power of alpha I could get when I multiply out the first few brackets is 1 less than a power of 2. If I take 1, 2, and 4, I've got 7. That's 1 less than the next power of 2. 1, 2, 4, 8 would be 15. So if I multiply out the first 4, I think I can get up to an alpha to the 15. And if I've got each sort of power of alpha, if I've got a coefficient of 1 on each of them, then when I multiply by the next bracket, I mean, the 1's going to keep everything nice. Alpha to the 8 is going to give me a coefficient of 1, and there's no overlap between the terms because the next power is alpha to the 8 is so big. It's just big enough that alpha to the 8 times this 1 is going to be a different power of alpha to 1 times this alpha to the 7. I suppose what I'm saying is every time you multiply out these another bracket, you get twice as many terms, but all the coefficients are 1. So I think this infinite sum is 1 plus alpha squared plus alpha cubed, and so on. I think we can get all of the powers of alpha. That's a geometric series. That is 1 over 1 minus alpha, which is equal to part C. It's the same expression in alpha. So this was a geometric series in disguise. At the start I said it wasn't a geometric series, and then it turned out it was. I think this is using something about binary to say there is an alpha to the 37 in here, and the coefficient of alpha to 37 comes from thinking about the binary expression of 37 and picking terms out of these brackets to make 37. Cool question. Okay, that's question 2. Okay, question 3, here's a curve sketching question. We're given these different functions. They've got a subscript k, but that's just going to mean which one of these it is. So when k is 1, this is going to mean f1 of x. The k is just keeping track of which one it is. Here, 1 over 1 is 1. So this is going to be f1 of x is just x for positive x, I suppose. f2 of x is supposed to be x to the 1 over 2, and f3 of x is x to the 1 over 3. Okay, part I asks us to sketch all of these curves. I'm going to try and do that over here. Okay, so this is going to be x. This is going to be, what do I want? I want y equals f of x. Okay, so I can put f1 of x on here straight away because that's y equals x. So I'm going to draw a nice 45-degree line, which I'm going to label f1 of x. Okay, then I've got square root of x. I know that square root kind of looks like this, right? It's very steep over here, and eventually I suppose it will be equal. I suppose it's equal. When is square root of x equal to x? Well, that happens when x squared is equal to x, which happens when x is 0 or x is 1. So I need to draw a shape like that that goes through x is 1. There's an intersection point here at 1, 1. That is y is f2 of x, x to the half. Okay. X to the 1/3, I'm going to have trouble threading the needle here, getting x to the 1/3 in, because I think x to the 1/3, between 0 and 1, it's also going to be between 0 and 1. I think that continuing this pattern, x to the 1/3 is bigger than x to the half. Let's just check that. So I think if 0 less than x less than 1, then x to the 1/3 is bigger than x to the half. Well, am I right? Let's check. Let's do both sides to the power of 6. Both sides to the power of 6 will get rid of all those powers. So it's x squared bigger than 6 is x squared bigger than x cubed. If x is between 0 and 1, then this side's got an extra factor of x. So it's smaller. X is less than 1. Yes, okay, that's true. So x to the 1/3 is bigger between 0 and 1, but then I think it's smaller afterwards. Similar reasoning, I suppose. So I've got to draw something that's bigger here and then smaller over there. Let's give that a go. I suppose it's very steep as well. Oh, there we go, that's perfect. Also going through 1, 1, because the cube root of 1 is also 1. And I suppose all of these go through 0. Those are my intersection points. I think that's all of them. X to the 1/3 equals x when x is 0, we're positive 0 or 1. Yeah, I think that's all of my curves. Part 2 asks us for the area between y equals fk of x and y equals fk plus 1 of x. And there's this method for finding the area between two curves where you take the difference between the upper curve and the lower curve. So to find this area, I just do f2 of x minus f1 of x and integrate that. To find this area, I would do f3 of x minus f2 of x and integrate that. In general, I would do fk plus 1 of x. That's going to be upper one minus fk of x dx. Okay. In general, this is very hard to do, but here we know what fk of x is. So I can fill these in with what f actually is. And now the question is just to do the integral of these powers of x. They're not polynomials, but you can integrate them in the same way that you know how to integrate polynomials. to get things like 1 plus 1 over 1 plus k over 1 plus 1 over 1 plus k, and over here x to the 1 over k plus 1 over 1 over k plus 1 between 1 and 0. Plugging in the limits, 0 is going to give me 0 for these terms, 1 is going to give me some powers of 1 on the top. That's going to be 1 over 1 plus 1 over 1 plus k minus 1 over 1 plus 1 over k. And I think you can simplify this if you multiply up by k plus 1 and also multiply this one up by k. Then you can get something like k plus 1 over k plus 2 minus k over k plus 1, which then simplifies a little bit more if you make it into one fraction. That's equal to 1 over k plus 1 k plus 2. Okay, which when we're looking at the area between f1 and f2, k is equal to 1. So when k is 1, this is 1 over 2 times 3. 2 times 3 is 6. So this is 1 over 6, which is what they ask us to check. 1 over k plus 1, k plus 2, when k equals 1 is equal to, it's 1 over 2 times 3. It's 1 over 6. Okay, fantastic. Okay, part 3 brings in this constant c, which is somewhere between 0 and 1. It asks us to intersect the line y equals c with two of those graphs we had before, f1 and f2. F1, remember, was just x, so this is easy. These intersect when x is c and y is also c. That's the point, c. Over here we've got to do slightly more work because f2 was x to the half. So I want to intersect that y equals x to the half with y equals c. That happens when x to the half is equal to c. Which is when x is equal to c squared, and then y will be, well, c. So that point of intersection is going to be c squared c. I'm going to try and draw a picture of that. X, y. F1 was y equals x. F2 was the square root shape. They both went through 1, 1, so that's 1. That's 1. And c is some point in here between 0 and 1. With intersection points c squared c intersecting with f2 and just cc where it intersects with f1. Okay, part 4 wants us to find the particular value of c. You see it's broken this area up into two parts. It wants us to choose c so that those regions have equal area. Here's my plan. I suppose I could try and calculate both of these areas and set them equal to each other. That feels like a lot of work. Especially since we already worked out that the total area between f1 and f2 is 1/6. So I have to have 1/12 on each side if these things are going to have equal area. So rather than working out both and setting them equal to each other, I'm going to work out one of them and set it equal to 1/12. Okay, here's my plan. I've got a choice, I suppose. I could work out this one down here, or I could work out this one up here. I think what I'm going to try and do is work out the top one. I've got this plan, you see, that I could integrate f2 from here to here, and I'll need to do some subtraction because I just want this bit above the line. So I'll need to subtract off this rectangle and I'll need to subtract off this triangle, and then I'll be left with this area here. I haven't seen a shape quite like this before, but I think I can work out how to make it out of one integral and some shapes I recognise, like rectangles and triangles. Okay, so I'll need to do integral of x to the half from c squared up to 1. That's my total area, including the rectangle and the triangle. I'll need to remember to subtract off that triangle area and also that rectangle. Do I know where all the points are? Yes, this is c squared. This is 1, this is c up here, this is 1 up here. Okay, I know where everything is. Okay, when I do this integral, I'll get x to the 3 over 2, divide by 3 over 2, between 1 and c squared. That is 2/3 of 1 minus c cubed. Lovely. Okay, so that's the integral of x to the half between c squared and 1. I need to subtract that rectangle and the triangle, so I'll get 2/3 1 minus c cubed. I need to subtract, right, that rectangle has height c and width 1 minus c squared. And that triangle over there has base 1 minus c, and it has height 1 minus c, and it's a triangle, so divide by 2. All of that is supposed to be equal to 1/12. Okay, that's the fact I know. This is a cubic equation. I'm going to try and simplify it and hopefully get the cubic in the question. Wish me luck, let's go. I think we're going to fast forward through me simplifying this algebra. If I multiply that up by 12, I get 4c cubed minus 6c squared plus 1 equals 0. Oh, hooray! That is the cubic that they wanted. It says, final part of this question, hence find c. I can't think of any clever ways to find c from this cubic equation other than guessing a root, guessing a solution. 0 is not a root, 1's not a root. I guess it has to be somewhere between 0 and 1. I've got to start guessing numbers between 0 and 1. The first number I guess is c equals 1/2. And it turns out that makes this first term into 4 over 8 is 1/2. So 1.5. Minus this 6 over 4 is also 1.5. So c does equal 1/2 for that final part of the question. Put it in the middle to split it into equal areas. Who'd have guessed? Right. Okay, question 4. This question's got a lot of different parts, and some of them are about horses. So we've got a square field of side length 1, and in the first part of the question, there's a horse that's attached by a rope to the corner. So I suppose it can reach, if it stretches the rope out taut, it can reach, maybe it can reach some quarter circle of the field, if it gets the rope as long as it goes, and walks around in a quarter circle like that. I suppose if the rope is longer than the side length, then maybe it can reach a little bit further and it's not a quarter circle anymore, but I've got a feeling that then it could reach more than half the field. For the first part, I just want it to reach half the field. So I've got this unknown radius of the circle, and I'm going to give this a go. I want r to be less than 1 for my picture to make sense. What do I want? I want this area inside here to be 1/2. Total area of the field is 1. I want, what do I want? I want pi r squared over 4 to be equal to 1/2. Area of a circle divided by 4 to be 1/2 of the field of size 1. So I want pi r squared to be 2. I want r to be root 2 over pi. And that is less than 1, so this picture does make sense. That's the length of rope that lets the horse reach half the area of the field for part 1. Part 2, there are now 2 horses attached to opposite corners of the field, and they each have a rope that has that length root 2 over pi. So this horse can reach some area over here, and the other horse can reach some area like this. Okay, explain why the area that both can reach is the same as the area that neither of them can reach. That's an interesting thing to ask, isn't it? So I suppose if we call this area A, and then the other bits of area between them B, we're trying to show that A equals B. Well, what do I know? I suppose I've got these other 2 bits of area, C, that are equal. If I'm giving my areas names, I should have these ones as well. Now, both the horses, each horse can reach half the field. So I know that A plus C is equal to 1/2, half the field. And I suppose I also know that all of these areas added together, the point of B, that's both of these bits. Maybe I'll have B as, actually I've changed my mind, I'm going to have B as each of these bits. This bit's B, this bit's B. I think that makes more sense for the picture. Then I suppose I know that the area overall is going to have A plus 2C plus 2B is equal to 1. That's quite good. So can I rearrange this to tell me that B is equal to C? That's my goal. Or 2B is equal to A or something. That would mean eliminating C. So I'd take this one and I'd write C is equal to 1/2 minus A. I'd plug it in here and I'd get A plus 1 minus 2A plus 2B is equal to 1. The 1's cancel. I lose some A's and I can move an A over to the other side. So A is equal to 2B. Fantastic. This area in the middle is equal to 2B, the spotty areas on the outside. So the area that both can reach is the same as the area that neither can reach. I suppose you could think about adding together the areas that each horse can reach. You've double counted the area that they can both reach. And you've got the number 1 because they can each reach half the field. You could also get 1 by looking at the total area and thinking about the area that neither of them can reach. Okay, right, good. Part 3 asks us to actually work out that area that neither of them can reach by finding this angle, and that's the angle from that line between the two horses to this point where those two curves meet. Okay, so there's some sort of isosceles triangle going on here, isn't there? Because we could draw another line in here. And then what do we know? We know, I think, all the side lengths of this triangle. 2 of them have sides radius, that radius that we found for the rope, root 2 over pi. And the other one has length root 2 because it's the diagonal of that square of side length 1. Okay, that was the whole length, side length of the square was 1. So that's root 2 along there. Okay, so I've got a triangle with root 2 along this side. It's got 2 sides with quite an ugly length, root 2 over pi. And it's got angles alpha here and here. This, I want something in terms of the cosine of alpha. I think this looks like the cosine rule to me. This looks like I should write down some statement that says opposite squared is equal to b squared plus c squared minus 2bc cos alpha. And then if I rearrange that, I'll get, well, these 2 over pi's will go away, and I'll get, I can divide by 2. Yeah, this is getting a bit messy, but I think I can write 2 over root pi cos alpha. So moving that root 2 inside, cos alpha is equal to 1. So cos alpha is only going to be root pi over 2. So alpha is inverse cos of root pi over 2. Okay, hence show, that's my value for alpha. Hence show that the area that neither of them can reach is something horrendous that looks a bit like something to do with alpha. Hang on, yeah, that is alpha. So show that this is 4 alpha over pi minus root 4 minus pi over pi. Okay, crazy. How am I going to find an area like that? I suppose something we had before was we found that area, we knew that area was equal to, these areas on the sides were equal to the area of overlap. The area that they can both reach is equal to the area that they can't reach. So maybe I could try and calculate this area of intersection between the circles. How would I do that? So I suppose I could look at that as being something like, I could draw this line in. Then I'm starting to make triangles and arcs and things, aren't I? What do I want? I want that bit there. So this to me looks like, I could have an arc of a circle. I could have part of a circle. Oh dear, terrible picture. Part of a circle minus triangle where I know the angles involved. Okay, in fact, because I've got an alpha over here, I could just think about this bit of area here and remember to multiply by 4 at the end. Okay, let's try and find that shaded bit of area there. So it's part of a circle. How much of a circle is it? Well, it's alpha over 2 pi. If alpha is measured in radians, it's alpha over 2 pi of a circle of area pi r squared, where r was 2 over pi. There's a lot of pi's in this expression. So that's the bit of a circle subtended by angle alpha up to the circle there. And then I need to subtract a little contribution here from this triangle that goes from the horse to the middle of the square to this intersection point. So I'm doing bit of circle minus a triangle. That bit of triangle, that's now a right angle triangle. I know this hypotenuse here is root 2 over pi. I know this angle is alpha, and I want, what do I want? I want this length. I want the area of this triangle, I suppose. So I want to find this side. I know is root 2 over 2. And this side is going to be something like, well, I can do Pythagoras on this, can't I? I can do Pythagoras to say this is 2 over pi minus 1 over 2 square rooted. Yeah, okay. So the area of this triangle is going to be, the area of this triangle is root 2 over 2 times root 2 over pi minus 1 over 2 all over 2. That's how triangles work. Okay, so I'm almost there. I need to simplify my expression quite a lot. These 2's cancel, some of these pi's cancel, and I'm going to have alpha over pi, this is the shaded area still, minus root 2 over 4, root 2 over pi minus 1 over 2. Let's try and decipher that bit a bit. That square root is 4 minus pi over 2 pi. There's a root 2 out here, so I could cancel this root 2 with this root 2 over here. And I get alpha over pi minus 1 over 4, root 4 minus pi over pi. Last thing I need to do is multiply by 4, because I've got 4 bits of this shaded area in here for the area of overlap. So multiply by 4. I need to replace this alpha with the expression we found for alpha, and I need to remember that the area of overlap is equal to the area that neither of them can reach, and that gives me the expression in part 3. Part 4, now there are 3 horses. One of them's in the top right corner, and the other 2 are on the sides, over here and over here. And they're given different bits of rope, and we're told they can access equal areas of the field. So I suppose that means there's different lengths of rope for different horses. This one you see can get to a sort of semicircle, so can this one. I suppose we'll put them on the same length of rope. This one could get to a quarter circle though. So if this one's on a length R, and this one's on a length, different length letter Q, then I suppose I need pi r squared over 2 to be equal to pi q squared over 4. This is provided that if r is less than a half and q is less than 1, so that they look like a semicircle and quarter circle. If that's the case, then I want, well, let's try and solve this equation. Q is going to be root 2 times r, I think. This horse needs to be on a longer rope so that it can access the same amount of field. Okay, none of the areas overlap, and we want to make Q and R big so that the horses can get to lots of the field. We want to minimize the area that the horses can't reach. Okay, so we want to make these shapes bigger just about to the point where 2 of them overlap. It's not obvious to me how that's going to happen. It could happen with this horse reaching kind of a situation like, well, like this, where that horse can reach lots of grass, and the other two, it starts to reach grass that the other two horses can reach, or whether these two horses can eventually reach grass at the same time. Let's try drawing the case where these two horses can just reach the same lovely bit of grass halfway through them, halfway between them. That would be somewhere over here. Then in that case, how big's that? So that's some particular size like that, and we'll have a semicircle over here. We'll have a big quarter circle, I suppose a big quarter circle that might get up to overlap. I want it to not overlap, like that. Okay, maybe it's the case that they just touch over there. If that's the case, then I've got a right angle triangle over here. I know this is 1/2 and this is 1/2. And in fact I've got some similar triangles going on, haven't I? So I know that this is 1/4. This little triangle is a 1/4 √2/4 triangle. So I want the radius that these ones are on to be √2/4. And then I want Q to be √2 times R is 2/4 is 1/2. So Q can reach up to 1/2. And then I suppose I need to check that this happens first. That it's not the case that I've kind of assumed in this picture that the Q horse in this top corner hasn't overlapped with the other areas yet. So I think I need to check that by thinking carefully about this distance. That is 1 plus 1/4 square rooted by Pythagoras, which is √5/2. And I need to check that that's bigger than √2/4 plus 1/2, which is what I'm planning to let the horses do if you allow for ranging this way and this one ranging this way. I'm hoping that those don't overlap. How big are these numbers? Well, √2/4 is less than 1/2, I think. Or √2/4 is less than 2/4. So this is less than 1, and this is bigger than 2. This is bigger than 1. So there's more gap between the horses than their ropes can extend to. Okay, worth checking that these areas don't overlap in this case. Okay, that's my answer. I want R to be √2/4 and Q to be 1/2. Okay, last part of the question. The horses are replaced by goats. I don't know why. They're attached to the midpoints again, and the rope length is G. Okay, there's a remaining horse. That's up here with a rope of length H. So that's doing something like this with a rope of length H, and we've got some goats over here with ropes of length G. Is that right? Same midpoints as before. Horses attached to the upper right corner with rope of length H. Given that 0 is less than H is less than 1. Okay, so this is a quarter circle. I've been worried about that for a while to make sure that this horse can't get around the corner over here when its area gets a bit strange. None of the animal's areas can overlap. Show that some inequality on G holds. I see. So before we said that everything could reach an equal area. Now we're not so sure. So before we had these goat areas aren't allowed to overlap, and that happened provided that the radius we saw before, we needed to have the radius, I suppose it's got to be less than what it was, √2/4. That's what we had in the previous part where the goats could just reach the midline. They could both reach that point halfway between them. If these areas are not going to overlap, I'm going to need G less than √2/4, which is, now that I think about it, that's 1/2 √2. Okay, that's this part of it done. Okay, G's got to be less than 1/2 √2, so that these goats can't reach the same bit of grass. Okay, so what's this other half of it then? We want to say that G is bigger than something. we want to see that this holds if the area that the animals can reach is maximised. So we're doing the same thing again. We're trying to let them reach lots of blocks. I haven't got the horse in here yet. I suppose if we're trying to maximise it, then we are going to make G big. We're going to make G as large as we can, right? So yeah, once you've maximised it, G's not going to be a small thing. G's going to be bigger than something. So what's the kind of worst case scenario for G? What's the smallest we might have to make G? Why can't I just make G 1 over 2 root 2? Whatever I'm doing. I suppose it could be a problem if H is too large, if the horse is roaming around. If the horse is roaming around in like its full range, H equals 1, then we've got a problem because the horse is taking up loads of space. And if the horse is taking up all of this space, and then we're not allowed to overlap, then the goat areas, well, the goats are going to have to behave a bit and keep to this area. So we're going to still increase G. We're going to maximise the area that the animals can reach by increasing G, and we'll get some particular value of G in this case. This is sort of the worst case scenario for the goats. Greedy horse eating all the grass. Worst case scenario for the goats here. Okay, let's try and find out what that length is. So I've let the horse have a rope of length 1, and I've got a right angle triangle over this side now. So this is G, this is 1/2 along the bottom. So let's draw that right angle triangle. 1 over this side, 1/2 over here, and 1 plus G along this side. So if I do some Pythagoras on this, I find that 1 plus G in this particular picture is equal to 1/4 plus 1 is 5 over 4. Excuse me, that's not how Pythagoras works at all, is it? 1 plus G squared is equal to 1/4 plus 1, which is 5 over 4. So G is equal to root 5 over 4 minus 1, which is root 5 minus 2 over 2. Okay, so that's the value of G in this case. If H is equal to 1, G is root 5 minus 2 over 2. If H is less than 1, can make G bigger, up to 1 over 2 root 2, at which point you run into the problem of the goats eating the same bit of grass. Okay, so none of the areas overlap. Different lengths of horse rope, you get different problems, and the value of G you pick to maximise the area the animals can reach is going to vary a bit between these values though. Okay, lovely problem. Horses. Okay, question 5. A teacher is handing out sweets. She gives the first sweet to child C1. She skips a child, gives a sweet to C3. And then she skips 2 children and gives a sweet to the next child, C6. She continues that pattern, so she's skipping more and more children each time she goes round. And the children are numbered 0 up to 9. Okay, so the question for part I is, where does the kth sweet go? Which child gets the kth sweet? And I think there's a pattern here that she gives the first sweet to C1, so she's moved one space around from C0, and then she's moving along two people, and then she moves 3 people along, and so on, until before she hands out the kth sweet, she's just moved K along. That sum is equal to K plus 1 over 2, which is this number. That's an arithmetic series to add up. K plus 1 over 2. Why is it the last digit? Well, there isn't a child with number K plus 1 over 2 when K is large. But she's going to go round and round the circle, so every 10 moves gets back to C0, so only the last digit matters. The last digit means ignoring multiples of 10. Multiples of 10 just loop around the circle. 37? No, actually you've done 3 laps and then gone to child C7. Okay, part 2 says suppose we look at a number between 1 and 18 inclusive. Explain why the kth and the 20 minus k minus 1 suites are given to the same child. We've got a formula now. We know where these suites are given. We know that the kth suite is given to the child with ci with last digit of k plus 1 over 2. So I suppose I just need to check that this one's given to the same child. That this one is given to a number with the same last digit, that child. Okay, who's it actually given to? Well, my formula says that I should look at 20 minus k minus 1. I should look at that, and then that plus 1. Okay. These numbers don't look the same yet, but I think I can do some multiplying out to say this is, well, this is a bit like 400 minus, it is multiplying out 20k minus 20k plus 1 plus k plus 1 all over 2. That is 200 minus 10k minus 10k plus 1 plus k plus 1 over 2. And this bit is a multiple of 10. Every term here has got a 20 or a 200 or a 10 or something in it. So that's a multiple of 10. It doesn't affect the last digit. Okay, great. So this doesn't affect the last digit. It just has the, so this is going to have the same last digit as k plus 1 over 2. Okay, so that's why the kth suite is given to the same child as the 20 minus k minus 1 suite. Part 3, let's think about what happens between the kth suite and the k plus 20th suite. The question asks us to show that those go to the same child. Let's think about how far the teacher walks in between those two suites. This is like thinking about the last digit and how the last digit changes. So after the kth suite, the teacher is going to move k plus 1 places along, hand out the k plus 1 suite, and then move k plus 2 places along, hand out the k plus 2th suite, and keep going. The teacher is going to move k plus 20 places along and hand out the k plus 20th suite. That's how far the teacher's moved in between the k suite and the k plus 20th suite. We'd like to show that the teacher is back where she started. Let's try and do this sum. This sum is, there are 20 terms in the sum, so I'm going to get 20 lots of k. And I've also got 1 plus 2 plus 3 plus 4 plus up to 20, which is 20 times 21 over 2. That's 210. So this is 20k plus 210, which means that the teacher has gone around the circle 2k plus 21 times and got back to the same child. So this is the same child. Okay, having gone around the circle quite a lot of times. Okay, the question asks us to think about which children can never get any suites. We've seen that after 20 suites, the pattern starts repeating again. So if you didn't get any suites in the first 20, then they're all going to the same kids again. So you've missed out now. All the remaining suites will keep going to those kids. And we also saw that you only have to think about the first sort of half of that set, because up to about 9 or 10, we know that there's this rule to say that early suites go to the same kids as later on. Like this says that the first suite goes to the same person as the 18th suite. It also says up to, I think, the 9th suite, when k is 9, goes to the same kid as the 10th suite. So that kid gets 2 suites in a row. So we just need to think about which kids are getting the first 9 suites. If we work that out, then we'll know who's getting the suites 10 to 18 as well. I suppose we need to think about suite 0, suite 19, and suite 20. And then after that, well, after now, the suites will start going to the same kids again. Okay, suite 0 Oh, it didn't exist. We did the suite. The first suite was suite number 1. It went to child 1. Okay, so no suite 0. But I will think about 20 when we get there. So 1 goes to child 1, and it's going to work out the last digits we saw in part 1. The important thing is the last digits of these triangle numbers, which I'll list now. So add 6, add 7, add 8, add 9. Those go to child based on the last digit 136051865. And then the 10th one would be 55, last digit is 5 again. So it's in 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th. And then the 19th suite, we're at child 1 now. We have 19 on the 19th suite. 19th goes to C0, and then the 20th goes to C0 as well. So at the end of that, child C1 has picked up this week 4 suites, because we do this on the way up, then we do this on the way down again for suites 10 to 18. So child 1 has picked up a few suites. Child 3 has got a few from over here. Child 2 hasn't got any, so C2 doesn't get any. C4 doesn't get any. It doesn't look like C5. 5 and 6 are fine. C7 hasn't got any. C8 has got some. C9 didn't get any either. So these kids, C0 is fine. These kids haven't got any suites. Okay. Next part of the question says the teachers, in a particular case, walked around exactly 183 times. So that's 1,830 moves. It's moved that far, and given the last suite to C0. So last week was C0. How many suites were there initially? Well, the moves are very closely linked to how many suites there are. We saw that the number of moves you do is k plus 1 over 2. So we want to solve k plus 1 over 2 is 1,830, which looks a bit like a tricky equation to solve. We can try and rearrange it a little bit. K is a whole number, so it might be guessable. 3660. What does that look like? That looks a bit like 60 squares to me, because it's a bit close to 60 times 60 would be 3,600. So I think k is 60, k plus 1 is 61. Those things multiply to 3,660. I think that means 60 suites. Okay, we've been around 183 times. 60 suites means that we've done 3 lots of 20 suites. We saw that was that pattern every 20 suites. Which children received the most suites, and how many did they receive? So we saw that pattern of what happens to the first 20 suites repeats. 60 is a multiple of 20, so it's repeated a whole number of times. I just need to find out who got the most suites up to the 20th suite. So in this thing we did before, who's got the most suites? Child 1 has got 4 suites, because they get the 1st, the 6th, then the 13th, and then the 18th. Child 0 has got 4 as well, because they pick up these 19th and 20th ones. Can anyone beat 4? So there's not 3. 3's only picked up a couple of suites. 6 has got 4 as well. 5 has got 4. So I think 4 of these kids, 8's only got a couple in each time round. But I think there's 4 of these kids who are getting 4 suites each go round. Shocking, 20% of the suites each. They are 1, 6, 5, and 0. 1, 6, 5, 0. They each received 4 suites each time round. And 4 suites each time round. We went around 3 times. They got 12 each. Okay, which is quite good going, given there are only 60 suites total. Right, okay, that's the end of the suites question. Okay, question 6. This one was featured in The Guardian recently, so you might have seen it there. This question is about stacking your shopping in some order and checking whether that stack is safe or not. Here's the rule. You look at each level, you look at the weight above. Here, the weight here is 5, and you compare that to the strength. So you look at the sum of the weights of everything above, and you compare that to the strengths of things below. So here 5 is bigger than 4, so this bread is going to get squashed because its strength is only 4 and there's a weight of 5 above it. At the same time though, with a weight of 9, total weight of 9, the carrots are safe. It's okay for the total weight to be the same as the strength. Okay, the strength of the apples here doesn't matter at all because there's nothing on top of the apples. Okay, so the apples are also fine, but squashed bread, bad news. Okay. The question wants us to know, the question notes that swapping the apples and the bread does give a safe packing. So if we had 4, 4, 5, 6, 12, 9, like this, bread, apples, carrots, then because 4 is less than 6, this middle item is happy, this top item is always happy, and the bottom item has still got a weight of 9 on it, and its strength is 9, so everything's happy. Okay. The question asks us about the other 4 orderings, but maybe if you've packed a shopping bag before, you know you probably want to put carrots on the bottom, and that's true here because the weight of the carrots is 12. The weight of the carrots is 12, and that will squash anything you put on top of it. That will squash anything else. Because the other things only have strength of 6 or 4, so it doesn't matter what else you put on top. You probably shouldn't put anything else on top, and even the carrots are too much to put on top of the apples or the bread. If we put the carrots at the bottom, we've already checked the 2 possibilities where the carrots at the bottom, so there are no safe options out of the other 4 with carrots not at the bottom. Those are all a bad idea. Okay. Next part of the question wants us to explore these packings in general. It wants to explore particular algorithms or particular strategies. So the next 2 parts of this question look at 2 algorithms or strategies that don't work, and they ask us to prove that they don't work. We're going to prove that they don't work by coming up with a shopping list for which the algorithm fails with disastrous consequences. Okay, so we're going to try and disprove the following algorithm, or show it doesn't work. So the tactic in part 2 is to put the items in weight order with the heaviest thing at the bottom. Show by giving an example. So I need to come up with some items and I need to come up with some weights. What do I buy when I go to the shops? Well, let's have eggs, and let's have crisps. I've tried to put fragile things because in my example they're going to get squashed. Okay, the strategy is to put the heaviest thing at the bottom. So I just come up with some weights for these things. And we've put the heaviest thing at the bottom. So I'm going to give the crisps a bigger weight than the eggs. I've given them 1 and 2 because I'm trying to use whole numbers but not make the numbers too big. Okay, the challenge here is going to be to come up with some strengths to show for these items to show that this is a disaster. Now the eggs are fine, they're on the top, so it kind of doesn't matter what I put here. I have to put some number here, I'm going to put like 5 over here. I suppose like some massive strength, doesn't matter at all. But I have to choose a strength here for the crisps that will make them get squashed. I'm going to put a strength of sort of 1/2 in here. So in this arrangement, the crisps have been squashed. Okay, might not produce a safe packing order. Oh, but now I've noticed that even if a safe packing order exists. Okay, so I need to show an example that my shopping's not just doomed. I have to show that sometimes this algorithm goes wrong, even though there was a workable solution. So I need to make sure, and I've still got, I suppose I wrote this 5 in here at random, but I could change that number if I wanted to. So if I put them the other way up, then the strength of the crisps doesn't matter anymore. I want this one to be an example of a safe packing that the algorithm missed. So I should make this strength nice and big. Putting a 5 in here was a good idea. Because if I put a 5 in here, then the eggs are safe with just the crisps on top. Okay, so this way around is fine. 2 is less than 5. This way around, 1 and 1/2, not okay. Even though we've put the heaviest thing at the bottom, because in this case the heavy thing was also quite fragile. So in part 2 we saw that stacking them in weight order doesn't always work, and in part 3 we're going to show that stacking them in strength order might not work as well. So I've got new items now. I've got chocolate and I've got juice, and I'm going to show maybe you try stacking these things in strength order. So maybe the juice has got strength 10, nice and sturdy, and the chocolate has got strength 5 or something. I don't know why I'm using multiples of 5. And now my challenge here is to set the weights of these items so that this packing order, where you put them in strength order, is no good, while meanwhile having them the other way round would be okay. So this algorithm in part 3 is the tactic is to pack them in strength order. I'm going to try and find an example with chocolate and juice where that doesn't work. Okay, what do I need to do? I need to make the weight of the chocolate bigger than 10 so that this packing fails. I'm going to make it sort of 20 over here. So that's my chocolate and juice. Oh, I'm supposed to swap the chocolate and juice in this one, aren't I? Okay. So that's 20. Okay. The weight of the chocolate over here doesn't really matter because it's at the bottom. And then I suppose I need to make the juice really light so that it's an example where this is a happy scenario. I'm going to make the juice weigh 1. And if I make the juice weigh 1, then over here, this packing is still bad news for the juice. But over here, this packing was fine. So sometimes stacking them in strength order doesn't work either. If you've got something that's very strong but also very light, then maybe you should have put it nearer the top. Okay, that's parts 2 and 3 to show these algorithms don't work. In the next 2 parts of the question, we're going to find an algorithm that does work. Okay, part 4 says, suppose we've got a safe packing order with item J directly on top of item I. I'm going to draw the stack. So there's some items above, maybe, and then there's something with weight WJ and strength SJ, and then it's directly above something like this, and there's maybe some items below as well. Okay, and we're also told, suppose further, that WJ minus SI is bigger than or equal to WI minus SJ. Show that if we swap them, we still have a safe packing order. Okay, so here's what we want. So we know this is safe. We also know WJ minus SI is bigger than or equal to WI minus SJ, a mysterious inequality. Here's what we want. We want to show that swapping them around is safe. Okay. Let's check whether this is safe or not. So, what have we got? Well, we could have some shopping above with some other weights, and I suppose some other strength values up here. Let's have some little S, S1, S2, dot, dot, dot. I suppose all of these are okay, and when we do the swap, so all of these items are shopping are fine. When we do the swap, everything up here is the same, so that's still okay. So that's fine. That bit of shopping's fine. The stuff below, it has some weights as well. So like W, I don't know, W, N, W, WN, more W's down here. More W's down here, but the weights don't really matter because everything down here is safe, and everything over here still has the same weight of stuff on top of it. It's in a different order now, but it's the same weight above, so that's fine. Okay, we just need to worry about these items squashing, I think. This one here, since this is a safe packing, what do we know? We know that W is less than, this big W, weight of everything above, is less than or equal to SJ. And I suppose we also know that weight plus this extra item is less than or equal to SI, that this thing doesn't get squashed either. Okay, those are some facts we know. We also know that All of these strengths are quite small numbers. That's fine. They're going to stay being. It's quite big numbers. We know they're going to be big numbers over here, big enough that nothing gets squashed down there. Okay, so we know these facts. The total weight of stuff above is less than or equal to Sj, and then even if you add Wj, you're still not as big as Si. That one's got some perhaps extra strength. Or maybe not. Maybe Sj was overly strong. It doesn't have to. Si doesn't have to be bigger than Sj. Right, we want to show that this is still safe. So we want W to be less than Si, and we want W plus Wi to be less than Sj for this stack to be safe. These are almost the same equations, but not quite. Okay, so I suppose if all the weights are positive, I'm thinking here, big W less than or equal to Si says that the shopping above isn't squashing a thing number I, and it wasn't squashing thing number I before. I think formally that's this inequality here means that even with Wj involved, you weren't squashing thing Si. So from here, you say so W is less than or equal to Si, since all the weights are positive. Okay, so W is less than Si. That's something that I wanted, since Wj is positive. All the weights of things are positive in the universe. Okay, what else have I got? I've got this inequality here, I've remembered. Okay, I've got W plus Wj is less than or equal to Si, and I've got this inequality, which involves kind of all of the things I'm interested in, and I want this. My plan is, I think, to try and add these together so that the terms I don't want go away. So I've got this Si on here. I want that to go away because I don't want Si in my final statement over here, and I also want the Wj's to go away somehow. We'll see if that happens. Okay, I'm just going to add these two inequalities together. So I'm going to do 1 plus 2 in the middle somewhere. Not a huge amount of space. I've been working inwards. Okay, so adding together the big sides, we get Wj minus Si plus Si. So it's adding together the large sides of these inequalities. That's big. That's bigger than Wi minus Sj. I've added them together, plus big W, this way, plus Wj. Okay, so actually I can rearrange this inequality a little bit. I've got a Wj on both sides, and I can move this Sj over to this side to say that Sj is bigger than big W plus Wi, which is exactly what I wanted. So this inequality was just the right inequality to add on to the one I had, so that this thing I wanted would be true. Together, these things say that this entire stacking is safe. So we're good. Even if we swap these items, we still have a safe packing order. Nothing's going to squash. That's part 4. Okay, for the last part of this question, we've got to have some sort of big idea about what's been going on in this question. We've seen a couple of algorithms that haven't worked. And now we're going to find a kind of algorithm or strategy for stacking the shopping that does work. We've got this observation that if you have a safe packing order, then you can swap items I and j if j was just on top of I and this inequality holds. So if we have a safe packing and we spot somehow that this holds somewhere for a pair of items, then we can swap them and we've still got a safe packing order. The idea of this last part of the question is to say, if a safe packing order exists, how are we going to find a safe packing order? Maybe we don't find every safe packing order, but maybe we can find a safe packing order. In a way, I think we want to prove that other packing orders are safe, given that some safe packing order exists. Let's use this swapping thing to try and find other safe packing orders until we get to one where everything's sort of nice and tidy, that we might say if a safe one exists, then this particular arrangement is safe, and I could actually construct that with my shopping. Okay, so the tricky bit is going to be spotting. If you give me a random stack of shopping, spotting whether this inequality holds or not. If this inequality holds, then I'm allowed to swap some items. I don't like the minus signs. That's feeling quite difficult. I'd like this to be kind of like a property about the shopping, like each item of shopping. So I'm going to try and move the SJs onto the same side as the WJ, and move the SI onto the same side as WI. Okay, so part 4 says, if you see some shopping, if J is on top of, oh, that's not one word. If J is on top of I, directly on top of I, and let's rearrange this, WJ plus SJ is big, if it's bigger than WI plus SI, then we can swap I and J, things I and J. Okay, so this says if you've got a safe packing and you notice that the weight plus the strength of one of the items is bigger than the weight plus the strength of the item just below it, you're allowed to swap them. I guess you're moving the one with the bigger weight plus strength down. Okay, so then we could do it again, I suppose. If we had something with massive weight plus strength, something with the biggest weight plus strength in the stack, then it would definitely satisfy this. Okay, so let's say, suppose you've got a safe order. I didn't really understand when this inequality would hold, but I've got an idea about when this inequality, this equivalent inequality, when this one holds. Suppose you've got a safe order. Find the item with biggest weight plus strength. Then it's definitely on top of something with less weight plus strength, directly beneath it, so we can swap it. We can keep swapping it down. So swap it to bottom of pile. We can keep swapping it down because every time it will have bigger weight plus strength than the item just below it. So keep swapping it down until it's at the bottom. Now repeat with the item. So I want to do that again. I want to repeat with the item with next largest, W plus S. Since we're doing this sort of swap that keeps the pile safe, then, and keep doing this. Yeah, keep going. The pile we end up with will be safe if you're doing the sort of swaps that start from a safe packing order and give us a safe packing order, and will be in order of weight plus strength. Said another way, if a safe packing order exists, then you might as well put them in order of weight plus strength. If there's any safe packing order at all, then you could rearrange it so that they're in weight plus strength order. So a practical method to find a safe packing order, if one exists, if one exists, would be to just put them in weight plus strength order. Stack them up, weight plus strength order from the one with the largest value up to the smallest. If anything was going to work, if there was a safe packing order at all, then this one will work. And this is a safe packing order. There we go. So we found a safe packing order. Let's quickly check that the ones we had before. So here, 6 and 2.5. I suppose these ones there was no. These ones there was a safe packing order. And the answer was to put 6 weight plus strength below 2.5. That was one way to do it. Here 25 below 11 was good. Over here, I suppose we could look at this shopping and say, well, if there's a safe order, then I want to put them in order. Weight plus strength is 21 here, it's 8 here, and it's 11 here. So I want to go carrots, apple, bread as the only one I want to try because it's the quickest to assemble with that quick test. If there's a safe packing order, then this one works. And in fact, we saw earlier that one does work, and it's actually the only one that works for that particular array of shopping. Probably more follow-up questions you could ask about that. I really like this question. Okay. We're given some operations that a computer can do on lists of numbers. Given two lists, it can join them together, which means placing list B after list A to do A plus B. I suppose it might be important that the order matters here, that A plus B is not the same thing as B plus A. For this example, B plus A would mean you put the second thing after the first thing. So B plus A would be 5, 6, 7, 1, 2, 3, 4. So if you're given the things in the other order, then they come out in the other order. We can also reverse sequences, putting them in reverse order like that. Okay, and the question is, given two sequences A and B, to express the reverse of the join as the join of two sequences. Wow. Okay. So I'm going to draw diagrams, I think, for this. If I've got my two sequences A and B, maybe A is a chunk of numbers like this with commas like this. This is A, and I've got B like this, going this way. Then A plus B means write both of those like that, and then R of that is going to reverse this. So start at this end, start with the end of B, and then work backwards through A. Okay, so that's going to be R of B plus R of A in that order. When you reverse this join, you're going to start at this end, that's the end of B, so it's going to be R of B comes out first. Okay, the other part of this says, what happens if you reverse twice? Reverse, you get back to where you started. You get back to A. Okay, now it defines a shuffle. So given a sequence A of length n and some number k between 0 and n, the kth shuffle moves the first k elements to the end in reverse order. So for example, this one takes the first two elements, puts them in the end backwards, and everything else shifts up. And this S3 means shuffle the first three, so they're going to go to the back in reverse order, and 4, 5 are going to shuffle up to the front. Okay. This would like us to think about the shuffle of A plus B, where A and B are both of length k, so exactly the right length for this shuffle. It's going to take A plus B as the join, so it's going to take these two sequences A and B, like this with a comma, and it's going to shuffle, moving the first k elements, which is precisely those ones that are in A, it's going to move them to the end backwards. So this is going to end up with B, and then A going backwards, which I would write as B plus the reverse of A. That's what the shuffle does. Okay, this part says, what is SK of A plus B? What happens if you do this twice? Well, we've just seen that if you do SK to A plus B, you get B plus R of A, and here I think it's maybe important that B is also of length k, because now we're going to do the shuffle moving these k items from the front, putting them at the end in reverse order. So this is going to be R of A, these items move up to the front, and B gets reversed and moved to the end. So this is a nice bit of question where A and B both of length k, so when the shuffle flips one of those around, it does that to the whole section. Okay, part 3 says, think about these numbers, 1, 2, 3, 4, 5, 6, 7, 8. Write down S5 of S5 of A. I'm going to work this out one thing at a time. So I'm going to do S5 of A first. That says take the first 5 items, so shuffle up the rest, or move the rest forwards, and then take the first 5 items and write them backwards. Okay, and then do it again. So now I want to work out S5 of that. So take the first 5 items, we're going to write those backwards at the end, and move the others forwards. So this is going to be 4, 5, 8, 7, 6. Okay, they would like us to write this as the join of 3 sequences that are either in order or in reverse order. So I suppose I can see this 3, 2, 1 is like the reverse of 3 sequences that are either in... Okay, so the join of 3 sequences that are either in order or reverse order. So there's a 3, 2, 1 here, there's a 4, 5, and then there's a 8, 7, 6 at the end. So some of these are in reverse order and some of these are forwards. Okay, I suppose we've taken the first 3 elements. If I look at what's happened when we do S5, S5, if I had to describe it in words, 4 and 5 are where they started, the last three numbers have flipped and the first three numbers have been reversed. Okay. Oh, and the question says, show that the sequence A is back in its original order after 4 S5 shuffles. 4 is 2 plus 2, so doing S5 4 times is like doing S5 twice and then doing it twice again. So the first 2 S5 shuffles get us to here, and then the next 2 S5s, ooh, terrible notation, S5s, are going to do the same sort of thing. They're going to flip the first 3, leave the middle 2 items alone, and then flip the last 3. It's also possible to go and work out S5 of this sequence and then S5 of that again, if you want to just work out what happens when S5 happens 4 times in a row. But somehow I like using the fact that I can see what S5 does if you apply it twice, and using that result twice. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8. This is A. Okay. Part 4 says, if SK is such that K is bigger than or equal to N over 2, so more than half of the elements are getting shuffled around, prove that after SK is performed 4 times, that the sequence returns to its original order. Okay, wow. I think I want to try it out a bit on some blocks. So if K is bigger than N over 2, that's what was going on here, right? K was bigger than N over 2, because 5 is bigger than 4. And we did it 4 times, we got back to where we started. Let's try drawing some pictures of what might be going on. So when I apply SK the first time, it'll take the first K items, K is more than half of them, and it'll split the sequence up somewhere over there. So this will be N minus K items over here. SK of this lot is going to take those K items and write them backwards at the end and move the other items to the front. So when I do SK twice, this original sequence, not sure if this picture is super helpful, but whatever. It's going to take the first K items here, and it's going to reverse them and put it on the end. What's that going to do? So it's going to take this N minus K block, that's going to end up at the end. So this is the kind of short N minus K block. That's now backwards at the end. Then there's a bit in the middle, perhaps, of overlap that's now forwards. And then it's going to move the rest of this. So this is the start of the K block. Over here, it's going to be now backwards. With this being sort of the one end of this is here, and then it's here, and then it's here. So I think from my scribbly picture, I think that something similar is going to happen, where it reverses the first few items. Maybe this is N minus K items. It reverses the last N minus K items, and the middle section stays the right way around in the middle. And I think if you put some algebra in, you can demonstrate that that is what's going on for SK happening twice to this sequence. Okay, if that's the case, then doing SK 4 times, so 4 times, we'll flip the first section twice, and we'll get back to where we started. This bit has been left alone twice, and this last section will be flipped twice by doing SK twice, twice. So we'll get back to where we started. I think that's the idea for part 4. Actual algebra would be a little bit tricky to fill in to work out what's going on. Okay, I'm back with some algebra. I think we can come in and give these sections names. And since there's a split going on and I'm interested in these different sections, I'm going to give them names. I think I want to call them like A, B and C, where A has length N minus K, so this has length N minus K. This one has length N minus K as well, and the bit in the middle has whatever leftover length it needs to have. I suppose that's 2K minus N, so that the total length adds up to N. I've chosen the length of B there very carefully. I think that's right, because then the length of A plus B will be exactly K. So when I do my shuffle, I can sort of see what's going to happen. Okay, if you write it like this, A plus B plus C, so you take your n elements and write them down like this, then when you do the first SK, you get, so SK is going to take us to, it's going to flip these two around and leave C at the front, yes, plus R of B plus R of A, when it flips around B and A. SK twice, so when SK happens the second time, it's going to this bit now. So this bit, C has length n minus k, and reverse of B is still length 2k minus n, so this bit has length k as well. Okay, so the second SK is going to come in, it's going to move the R of A bit to the front, and it's going to reverse these things. So we're going to end up with B in the middle, R of A at the front, and R of C at the back. This is great because now it's once again set up to have a bit of length n minus k at the front and the end, and a bit of length 2k minus n in the middle. So then SK 4 times will get us to R of A plus B plus R of C, which is A plus B plus C, which is where we started. So that's maybe the algebra we needed to do to split up part 4. Okay, last part. If k is less than n over 2, the sequence doesn't have to get back to its original order after doing SK 4 times. Let's try an example. I'm going to use small numbers. I'm going to try k equals 1 and n equals 4. That gives me the inequality 1 is less than 2, which is true, and use the small numbers. Let's find out what happens when I do S1 to a sequence with 4 items. I might as well take my 4 items to be 1, 2, 3, 4. So if I do S1 to that, it'll move the first element to the end in reverse order, but since there's only one element, the reverse of 1 is 1. Then if I do S1 again, it'll move that 2 to the end and shuffle up 3, 4, 1. I wonder what will happen after 4 times through. 3, 4, 1, 2. It's going to take me to 3 will go to the end, and the other elements will move up 4, 1, 2. And then S1 one more time to 4, 1, 2, 3 will give me, I'll move the 4 to the end and get 1, 2, 3, 4. So that is where I started. So this is an example with k less than n over 2 where it does get back to where it started after 4 times. Okay, so that was my first attempt. That hasn't quite worked. Maybe my next attempt, if I make k bigger, 2 and 4, no, that doesn't work. 2 is the same as 2. I can make n a little bit bigger. I still want to use small numbers, right? So I'm going to try k equals 1 and n equals 5. I've seen this S1 seems to just shuffle the element to the end, so I'm sort of hoping that this will take 5 goes to get around again. So if I do this, then that'll just move the first element to the end. So actually doing S1 4 times, it wasn't useless doing it with n equals 4 because I worked out how S1 works. It's going to move the first 4 elements to the end, and I'll get this. I'm being lazy and not writing all my commas. There we go. Which is not where I started. This one needs one more S1 to get back. So in this particular example, it's taken 5 to get back to where it started. You can imagine having more elements, so for large values of n, I could have got a different answer. It might have needed more and more shuffles to get back to where it started. So your example might have a different value of k, a different value of n, and it might take a completely different number of shuffles to get back to where it started. This is an example of something called group theory. We're looking at the order of the group. And in general, it's a little bit tricky to work out the order of an element of a group. More on that if you study maths at university. And that's the end of Math 2017. Thanks for watching.